All right, here's electric field notes. This is part 2. The electric potential energy of a charged particle is increased when work is done to push it against the electric field or something else that is charged. Work is done when a force moves something in the direction of the force. An object has potential energy by virtue of its location, say in a force field. For example, doing work by lifting an object increases its gravitational potential energy. If in elevated position, the ram has gravitational potential energy. When released, this energy is transferred to the pile. So as you lift it up, cut the streak, the potential energy becomes kinetic energy. Similar energy occurs for electric energy. So if you look at it this way, where we did, over here we had this is gravitational potential energy. Now we're looking at electric potential energy. Because you see this is a plus charge and this is a minus charge. If you cut the line, they are attracted to one another. So you have potential and kinetic energy. A charged object can have potential energy by virtue of its location in an electric field. Work is required to push a charged particle against the electric field of a charged body. To push a positive test charge closer to a positively charged sphere, we will explain energy to overcome electrical repulsion. Work is done in pushing the charge against the electric field. This work is equal to the energy gained by the charge. The energy a charge has due to its location in an electric field is called electric potential energy. If the charge is released, it will accelerate away from the sphere and the electric potential energy transferred into the kinetic energy. So you see what we have here? We have positive charge and positive charge. We have to do work, apply a force to move that positive charge closer, because what does the positive charge want to do? It wants to repel away. So if he lets go, it's going to shoot away from those other positive charges. How can you increase the electric potential energy of a charged particle? Work. Electric potential is not the same as electric potential energy. Electric potential is electric potential energy per charge. This is the important part. If we push a single charge against an electric field, we do a certain amount of work. If we push 2 charges against the same field, we do twice as much work. 2 charges in the same location in an electric field will have twice the electric potential energy as 1. 10 charges will have 10 times the potential energy. It is convenient when working with electricity to consider the electric potential energy per charge. So we look at each one individually. The electric potential energy per charge is the total electric potential energy divided by the amount of charge. At any location, the potential energy per charge, whatever the amount of charge, will be the same. The concept of electric potential energy per charge has the name electric potential. So electric potential is our electric potential energy divided by the charge. An object of greater charge has more electric potential energy in the field of the charged dome than an object of less charge, but the electric potential of any charge at the same location is the same. The SI unit of measurement for electric potential is the volt, named after the Italian physicist Volta. The symbol for the volt is the V, capital V. Potential energy is measured in joules, and a charge is measured in coulombs. A potential energy of 1 volt equals 1 joule of energy per coulomb of charge. A potential energy of 1,000 volts means that 1,000 joules of energy per coulomb is needed to bring a small charge from very far away and add to the charge on the conductor. The small charge would be less than 1 coulomb, so the energy required would be much less than 1,000 joules. To add on 1 proton to the conductor would take only 1.6 times 10 to the negative 16th joules. Since electric potential is measured in volts, it is commonly called voltage. Once the location of 0 voltage has been specified, a defined value for it can be assigned to a location whether or not a charge exists at the location. We can speak about the voltages at different locations in an electric field whether or not any charges occupy those locations. Rub a balloon on your hair and the balloon becomes negatively charged, perhaps to 1,000 volts. The charge on a balloon rubbed on your hair is typically much less than a millionth of a coulomb. Therefore, the energy is very small, about 1,000th of a joule. A high voltage requires great energy only if a great amount of charge is involved. If there were twice as much charge on one of the objects, would the electric potential energy be the same, or would it be twice as great? Would the electric potential be the same, or would it be twice as great? All right, key thing here. Twice as much charge, which caused the object to have twice as much electric potential energy, because it would have taken twice as much work to bring the object to that location. The electric potential would be the same because the electric potential is the total electric potential energy divided by the charge. What is the difference between electric potential and electric potential energy? The energy stored in a capacitor comes from the work done to charge it. Electrical energy can be stored in a device called a capacitor. Computer memories use very tiny capacitors to store the ones and zeros of the binary code. Capacitors in photo flash units store large amounts of energy slowly and release it rapidly during the flash. Enormous amounts of energy are stored in banks of capacitors that power giant lasers in national laboratories. Flux capacitor. Who remembers that? The simplest capacitor is a pair of conducting plates separated by a small distance but not touching each other. Charge is transferred from one plate to the other, the capacitor plates that then have equal and opposite charges. The charging process is complete when the potential difference between the plates equals the potential difference between the battery terminals, the battery voltage. The greater the battery voltage and the larger and closer the plates, the greater the charge that is stored. In practice, the plates may be thin metal foils separated by a thin sheet of paper. This paper sandwich is then rolled up to save space and may be inserted into a cylinder, like these. These are some examples of our capacitors. A charged capacitor is discharged when a conducing path is provided between the plates. Discharging a capacitor can be a shocking experience if you happen to be the conducting path. The energy transfer can be fatal where voltages are high, such as the power supply in a TV set, even if this TV set has been turned off. The energy stored in a capacitor comes from the work done to charge it. The energy is in the form of electric field between its plates. Electric fields are storehouses of energy. Where does the energy stored in a capacitor come from? The Van de Graaff generator. We will be working with one of these in class. The voltage of a Van de Graaff generator can be increased by increasing the radius of the sphere or by placing the entire system in a contained field with high pressure gas. A common laboratory device for building up high voltages is the Van de Graaff generator. This is the lightning machine often used by evil scientists in old science fiction movies. In a Van de Graaff generator, a moving rubber belt carries electrons from the voltage source to a conducting sphere. And I will explain all of this in class, showing you how all of this works. A large hollow metal sphere is supported by a cylindrical insulating stand. A rubber belt inside the supporting stand moves past metal needles that are maintained at a high electric potential. A continuous supply of electrons is deposited on the belt through electric discharge by the points of the needles. The electrons are carried up into the hollow metal sphere. The electrons leak onto metal points attached to the inner surface of the sphere. Because of mutual repulsion, the electrons move to the outer surface of the conducting sphere. This leaves the inside surface uncharged and able to receive more electrons. The process is continuous, and the charge builds up to be a very high electric potential, on the order of millions of volts. The physics enthusiast in the dome of the Van de Graaff generator are charged to a high voltage. A sphere with a radius of 1 meter can be raised to a potential of 3 million volts because electric discharge occurs through the air. The voltage of a Van de Graaff generator can be increased by increasing the radius of the sphere or by placing the entire system in a container filled with high-pressure gas. Van de Graaff generators in pressurized gas can produce voltages as high as 20 million volts. These devices accelerate charged particles used as projectiles for penetrating the nuclei of atoms. How can the voltage of a Van de Graaff generator be increased? These are the end of electric field notes.